Everything that you're going to see today has been open sourced. So if you would like to actually download the code and get a copy of these slides, please visit this GitHub URL and you can browse all of this. So a little bit about me and who I am. I was hired into LinkedIn in 2010. When I came into the company, we were around 300 machines at the time, and we knew we were about to have explosive growth. Since I came in, we've grown about 100 times that original size. And to address some of the issues we had with automation, in 2012, I designed this system built around CF Engine and Redis. So what is Redis? I'm sure you guys are familiar or have heard of Memcache. Memcache is a simple in-memory key value store. And Facebook used this to offload database queries. So a web server, instead of querying a database, would try to hit a Memcache node beforehand, and if not, it would actually hit the database. But this is kind of how you try to scale backend. So Redis is somewhat similar to Memcache, but it offers some additional things. The most important to us is basic data structures. So with Memcache, you just have a string and a value, and if you want to build anything complex above that, you kind of have to build your own data structures using this string key value. But with Redis, you get dictionaries or hashes, lists, sorted sets, etc. And these are extremely valuable. And it also offers persistence. So with Memcache, if your machine reboots or whatever, Memcache shuts down, you lose the entire cache. Here it's persistent, so we're taking snapshots to disk. You can actually use this as a database. And another really important feature is this concept of transactions. And a transaction is, I can send the server a single request, and that request may have 5 commands, and the server executes them at once instead of having to do this back and forth communication. So what is CF Engine? CF Engine is an automation framework that helps us manage our infrastructure at LinkedIn. We use it to push changes. It provides auditing, lets us know when things aren't being enforced. And it's very scalable. So it runs on from cell phones to embedded devices, desktops, mainframes, big iron. What's really powerful about CF Engine is that it's given LinkedIn horizontal scalability. So we can scale to tens or hundreds of thousands of machines. A little bit of a background of how CF Engine works. There's a policy hub, and the agent basically runs on every single host, contacts the policy hub, and downloads additional policies. Once this policy has been deployed, the agent basically executes that policy and executes change locally. The important thing here is that it uses the network when it can. So if the network link is severed, policy executes on the client, there's really nothing bad that happens. As soon as the network connection is restored, the client again can download new policies and execute new changes. So why use CF Engine? What we have found is that using CF Engine automation was much more effective than scaling headcount on our team. It gave us the ability to stay ahead of the curve and stop fighting fires, and it allowed us to focus on tomorrow's problems and scaling. Once you have some automation built, keeping the lights on basically just comes for free. It also allows you to respond to change very quickly and respond to outages. So why specifically did we choose CF Engine? Extremely mature code base. CF Engine was originally designed in 1993. We're not dependent on an underlying virtual machine, and this was pretty important to us. So we wanted to know that when we upgraded CF Engine versions, the only code changing was CF Engine itself. We didn't want to have to worry about a Ruby upgrade or a VM underneath our automation platform causing change. We can easily scale upwards and build data centers with tens or hundreds of thousands of machines, but we can also scale down very easily to support a point of presence with maybe 10 machines. It's had 0 reported vulnerabilities, so that's a pretty big bonus, and it's also a very lightweight footprint. It's completely written in C. So what has CF Engine done for LinkedIn? we can, as an operations organization, we can very rapidly respond to changing business needs. We can respond to outages and resolve them very quickly. And we've become extremely agile. So what used to take us literally a day to push 1 or 2 changes across our infrastructure, we're finding ourselves modifying production 10 to 15 times a day. Our systems have actually become very reliable. And one really added bonus from this is we can actually start delegating root access to developers. And as soon as you say that to system administrators, they kind of freak out. But what CF Engine does is, if you enforce via policy that, for example, resolve.conf, even if a developer goes in there and tries to mess it up, as long as you know that your hosts are checking into CF Engine, the machine will converge back to its known good state as it was designed in policy. And even in the worst case scenario, your engineers or developers screw up their machine with root access, rebuilding and reprovisioning is pretty much instantaneous. So how have we used CF Engine? Everything at LinkedIn is completely automated. What we are starting to find is that we are no longer logging into machines to manage them. I come across machines that we have had in production for 4 to 6 months, and it literally has 2 logins, and that was me when I built the machine. So we've taken all aspects of configuring the OS, monitoring for hardware failure, account and maintenance, privilege escalation, software deployment, system monitoring, literally everything that LinkedIn Operations does, we have automated with CF Engine. One really good bonus about this is that we can build data centers extremely fast. Usually, some organizations, it may take them months of planning. We can literally stand up new data center in minutes, if not hours. So automation is great, but we still had 2 very big problems that automation did not solve. The company needed to be able to answer any question about production. And we didn't want to break production by pushing changes. And this is a very scary thing for people who are trying to use automation for the first time. So we can enforce system state, but it was very hard to answer questions from tens or hundreds of thousands of machines. Automation doesn't give us visibility, but it gives us the tools to build it. And as our scale and size increase, collecting this information and getting visibility becomes a more difficult problem. So the first problem, the company needs answers right now. So your engineers are coming to you and they're asking, what software is installed? Are all the machines in Data Center X running the same version of OpenSSH? What processes are running? Who has a network connection to machine X? What hardware characteristics do I have on all of my web servers? How much RAM, CPU, etc.? What machines around me are connected to the same network switch? So you can see there's literally endless amounts of questions that you can ask about your infrastructure. And to try to answer this, we ended up hunting for data. So I found myself trying to SSH and connect to tens and hundreds of thousands of machines every day, 3 or 4 times. And I wasn't really working on business problems. I was just trying to get information. And so when I was pushing automation or trying to answer these questions, I wasn't going to break anything. I needed a system that I was able to quickly and reliably get results from so I could push these automation changes or I could assist management or engineering. So this is kind of what we were doing. We were SSHing to machines. Once we got to a certain scale, we started to use a tool called DSH. There's several open source equivalents out there. But basically, this tool is just taking an SSH connection and it parallelizes it across maybe 80 or 100 connections at a time. This has problems, though, because we don't know if we got the results from everything. Did the machine not make a connection, or for whatever reason, did I have too many outbound network connections? This took a lot of time. So what we ended up finding is we did miss machines. Firewalls got in the ways. The machine remotely didn't respond to SSH connections or whatever. And we ended up making changes without fully understanding the impact. So when we went to designing this, we thought data collection should not be complicated. I should not have to spend hours of my day trying to make sure I wasn't going to break something before I made a change. The second problem is we didn't want to break production by using automation. And no matter what automation product you use, whether it's CF Engine, Puppet, Chef, Salt, etc., they all have the same common problem, is that automation assumes that you know what you're going to do to your machines. And a lot of times administrators don't know. If you have 30,000 machines, you can write a policy and try to enforce system state, but if you don't fully understand your infrastructure, you can cause outages and you can break things. So we have to work fast. We have to make, like I said, 10 to 15 changes of production a day, but we can't spend hours trying to collect all of this data. So this is what was happening. We were pushing changes in the blind. So we had numerous ticket queues. Business was on our back trying to get things done, questions answered. And this really gets into a very dangerous territory when you're dealing with automation. Automation is a very beautiful thing at a company, but it's a very big hammer, and it can break things very fast. So you need to understand the impact of your change before you execute on it. So we had a data collection problem. We had to build a system that was extremely fast, and we can get results from tens or hundreds of thousands of machines in a second. So what we did is we built an in-memory cache with very commonly requested data. You don't really know what questions you're going to ask, so try to snapshot your machines. And the best example of this is Red Hat's SOS report, or Sun or Oracle. They have a product called Explorer. So when you're opening up a case with Red Hat, they're asking you to basically run the script, and Red Hat has no idea what's wrong with your system, right? So they're trying to snapshot the machine. Use these same commands and these same scripts to provide data to your company, because you have no idea what your engineers are going to ask. So provide upfront process tables, loaded kernel modules, mount tables, installed packages, user accounts, uptimes, load averages, anything in proc. Whatever you find yourself as a sysadmin looking at on a day-by-day basis to debug machines, insert it into this cache. So what we did is we have CF Engine executing on our machines, and it populates this cache with this commonly queried data. One advantage to this is that we can execute expensive commands once, and it's available for everyone to use. So when my engineers are requesting DMI to code against production 20 times a day, we're not putting impact on our end nodes. This basically becomes a regularly scheduled collection interval, and it's just a cost of us keeping the lights on. Another thing that kind of came out of this is it became very easy to compare two pieces of hardware, because we were collecting command output identical across all of our infrastructure. So engineers could very easily compare, the hardware characteristics on machine A versus machine B. So how are we going to build this? First, we rely on CF Engine execution to drive insertion. Don't centralize all of this data collection to one machine. What we have done at LinkedIn is, since we have thousands of machines, we have split up our CF Engine architecture, so many X number of machines responds to a single policy server. Query all of your policy servers to build your complete data set, and this is called sharding. Third, software load balancing here is critical, and it also provides failover, and we'll get to that here in just a moment. So at a very high level, this is what happens during CF Engine execution. A machine basically realizes that it has 4 CF Engine policy servers, and when CF Engine executes, it takes about 100 objects and inserts it into a Redis cache on each one of our policy servers. We collect executed commands or whatever arbitrary files off the file system we're interested in. Some of this data is inserted and collected at different intervals. So, for example, process tables change very rapidly. We want to update this at a 5-minute interval. DMI decode, hardware characteristics, if we execute this once a day, that's okay with us because usually hardware characteristics aren't changing that quickly. And from a very high level, this is what the cache looks like. The key is the name of the machine separated by the file name, and the value is a simple array. Array sub 0 is the contents of the file, and that's commonly what we're interested in. But what we do is on insertion, we also try to collect as much metadata about this file or this command as we can. So we collect MD5 sums, OSStat, word count, etc. If we wanted to collect any other metadata about this object, we would just continue to expand this array. So step 2, we have to extract this data. So sharding is a database design principle where your entire database isn't centrally collected on one machine. They're held on separate physical machines. With our database separated out over several physical machines, we get the added CPU, memory, and network capabilities of multiple servers when we go to extract data. And when we make a request, there's basically 2 actions we need to do. We have to match the keys that we're interested, and then we have to perform the relevant data extraction. So we need to use software load balancing. Since we're inserting into 4 Redis servers in parallel, all I have to do when I go to extract data is pick one of those Redis servers at random. If the first one doesn't respond, I can pick another one, and this gives us load balancing as well as failover. So like I said, we're going to find a randomized policy server running Redis at each stage of this architecture, and if it responds, we basically push it into a list of machines to query. So there's 3 levels of scope in this utility. Our first is local scope. So if you can imagine we're on this querying machine up above in cage 1 in data center 1. We have 4 policy servers, so we randomly just picked one, and that's all we need to do to fulfill this request. So local scope extraction is the default behavior of our utility that we built. And the reason why is that it returns the least amount of data, least amount of network overhead. It helps users kind of figure out how to use the utility, how to query it. It's the least amount of load on our Redis servers, and sometimes it's all that's really needed. So if I'm a web server and my web servers are around me, all I have to do is query my local policy server to build my complete working set. This is an example of the utility that we built executing. So we searched for the Etsy password file, and we ask to display the contents. So this is extracting array sub 0 out of the cache. I'm displaying Etsy password for all the machines in my core. I'm grepping for my host name, and I found myself in 487 machines, and this executed in a little over a second. The second level of scope is a site or a data center. So same idea as above. We're basically picking a randomized core or a randomized policy server from every core or every cage. And we just repeatedly do this for all of our policy servers at a data center. This could be a moderate amount of network overhead, and it could be cross-country traffic. So I could be trying to extract, for example, all hardware failures in Atlanta to a data center in Chicago. It's useful for auditing a particular application group, or say, all of my database servers in production. It drives multiple policy servers per site. Again, this is the same utility executing, searching Etsy password, looking at our Virginia data center. We found 8,600 instances of me in this file, and this executed in about 19 seconds. Finally, global scope. So again, we've repeated the same architecture that what we've seen before, but if you can imagine these long lines being a 3,000-mile wall between data centers, all we're doing is we're continuing to randomly pick policy servers from every cage of every data center to build our complete working set. The amount of data returned here is immense. this is literally global traffic. So if I have data center in Brazil, in Singapore, in Dublin, in China, in America, this utility is literally reaching out to all of our data center all over the world to build this working set. But this is really needed to answer some of the most basic questions that our engineers want to know. We want to know what version of CF Engine we have installed everywhere, or the version of Red Hat, or all of our RPMs are installed across all of our machines for auditing. This is driving multiple policy servers per site. The same example, searching through Etsy password, grepping for my name. I found myself in 27,000 machines, and we executed in 44 seconds. So how can we make this fast? We've sharded our data, and we're doing the exact same operation repeatedly to build our complete working set. So let's make this multi-threaded. There's two places where being multi-threaded helps us: when we're searching for keys and when we're extracting data out of our policy servers. Since we're doing the same thing across all of our policy servers, we might as well do it in parallel. The second thing we can do is we can build something called a Redis pipeline. A Redis pipeline is a subclass of the base Redis connection, and it supports buffering multiple commands to the server in a single request. This is used to dramatically increase the performance between the client and server. And the best concept of this is like a TCP sliding window. So if I'm going to extract 8,000 keys from a policy server, I send that policy server one request with the 8,000 keys, and the policy server responds all at once. We don't have to go back and forth 8,000 times between the machines. This is kind of an example of what a pipeline extraction will look like. So our query above is we're in a local scope. We're searching for mps*cm.conf, so our utility can support globs. And MD5 sum equals true, so this selects array sub 1. We found 4 objects in our cache, these 4 machines, and we basically send a single request for all 4 array elements at once. The utility executing, this is exactly what we just saw. We're displaying the 4 host names and the keys that we found, and their MD5 sum objects returned here. This is actually, while we're on this is an important concept here. So our compute power is at our end nodes. We have thousands of machines and literally hundreds of thousands of CPU compute cycles. So the reason why we populate as much metadata as we can on our end nodes is that when I want to do MD5 sum comparisons between thousands of machines, I just have to do simple string comparisons here. I don't actually have to compute the MD5 sums myself. Thirdly, compression really is significant. So we could insert the data into the cache in plain text, but there's really no reason why we need to. When we use compression, we use less network overhead on insertion. We can exploit the CPU horsepower on our end nodes. There's a lot less network overhead on cache extraction. And we're holding this stuff in RAM on our policy servers, and space is expensive. So the smaller we can get our cache on insertion, the more stuff that we can shove in there. And most importantly is if there's less data in the cache, it's actually faster to extract it. And what we found is this was kind of, we weren't expecting this, but we were thinking if we were going to have to decompress data on extraction, this would be a very CPU intensive action on the client. And what we ended up finding was the complete opposite. So instead of just reading text and just reading the cache in plain text, which was a lot of network overhead, it was actually less CPU for us to go through decompression algorithms and do less network I/O. And finally, we had an added security benefit of objects existed in the cache in binary form. So if you were a hacker, you could probably figure out that this is a BZ2 compressed object in this cache. But for script kiddie just scanning Redis caches, they're going to see junk. They're not going to see in plain text. So we evaluated 4 compression algorithms compared to plain text. So this is how much time it takes for a single client to execute our CF Engine policy and insert its data into the cache. Of course, plain text here is the fastest, but BZ2, zlib, and LZ4 are pretty close behind it. Again, CPU cycles for the client to insert data into the cache. LZMA here is pretty bad compared to the rest of them, but you can see plain text is pretty cheap. BZ2 is not too bad behind it. This was a pretty important graphic for us. So for our entire Atlanta data center, this is the size of the entire cache. In plain text, it was a little over 1.5 gigs. And in BZ2 compression, which is what we ended up selecting, we could shove everything in about 300 megabytes. And this is where we really saw the speed and improvements. So I extracted the entire Atlanta cache to our Sunnyvale data center. In plain text, it took me about 82 seconds. Using BZ2 compression, it took me about 23, 24. So it was almost a 300% increase just by compressing on insertion and then decompressing on extraction. And another thing to notice here is the user time. So you can see the plain text user time was 35 seconds or so. You can see here at BZ2 user time is significantly less. So there is less CPU overhead using compression. So drink from the fire hose. We have all of our data sharded here, and we're making parallel requests for it. So what becomes the bottleneck in this situation is the network connection from the requesting machine, because we're literally going out to, say, 30 or 60 Redis instances in parallel and pulling gigabytes of data down to a single machine. And this is why we didn't want to put a front end to this API, because a single request to hitting this cache can easily saturate a gigabit link. So if we have competing requests executing on the same machine, we'll have network starvation unless we move to a 10 gigabit or somehow re-architect the network. But we haven't put a front-end API to this. What we have designed is we designed a Python object called cache extractor. And the utility that you were seeing before, this extract sysops cache, was importing this Python object. But we use this cache extractor object in multiple utilities, and you can browse the code on the GitHub site that you saw before. So start off small in your request. For example, the Etsy password example we had. If I'm looking for a process, start my request in a local scope, and once I've extracted it and used grep sed awk to parse the data as I'm expecting, increase it to a global scope. So be confident, and this is what became really beautiful about this system for us, is that we became very confident in pushing change, and our management is confident in operations pushing automation change. We're not causing outages. We're not surprised in production. We know the impact of our change before we push it. You don't have to log in the machines anymore. And this was kind of a point in the keynote that you guys heard this morning, was how do we get people to stop logging in the machines? Well, this is a great example. You leverage automation to manage that for you. You use something like this to provide visibility, and this really brings you into the next generation of systems infrastructure. So just a summary recap. When I first started, we had 6 people on our team supporting about 300 machines. Now we're about the same size, but we're supporting tens of thousands. It used to take us around 8 hours to build a single machine, and it was an extremely error-prone process. And now we can literally light up complete data centers in minutes. Before, when we had to push a change, we had to audit production to make sure we weren't going to break something before doing it. And then we were trying to use DSH to make these changes, and we missed machines that were offline, and we just weren't productive at all. Now we're focusing on building higher level pieces of infrastructure. We're looking forward to tomorrow's issues. We're trying to figure out how to completely scale our platform even further. And again, it was very difficult for us to make changes before, and now we're pushing 10 to 15 changes a day, and our workload is actually decreased from before. So like I said, this is open source. If you would like to connect with me on LinkedIn, please, I'll be your social networking friend. But please, if you're interested in these slides or the code, please go to this GitHub address and feel free to contribute. So, thank you.
Okay, so now it's my turn. Let me see if I can exit this. There we go. Okay, my name is Diego Zamboni. I'm a product manager and security guy at CF Engine. And I just want to add a little bit of afterthoughts to what Mike presented from the point of view of CF Engine. Basically, I hope you all agree that what he has built is extremely cool. It's very useful. And the thing is that he's not alone in having built tools like this. Many people in larger or smaller scales have built this sort of data collection, inventory management, information managing capabilities at their organizations because it's a real need. I mean, you need to have some visibility into what your infrastructure is doing and what it looks like. So from the CF Engine point of view, it's not, CF Engine is meant to be a tool that integrates with the rest of the infrastructure that you have already. It's not meant to replace everything, but to complement and make your life easier as an infrastructure manager or infrastructure engineer. So what the goal that we set for ourselves was to make it possible for CF Engine to integrate with the sort of things that people were already doing. But at the same time, if you're starting up or you don't have such a system in place, to give you a nice starting point for this kind of capabilities. So basically, this is the architecture that we came up with. And this is coming live in the next big release of CF Engine 3.6, which is coming out in a few months. So basically, the idea is that the CF Engine policy server now also becomes a hub for inventory data and gives you a system for looking at, querying, and managing that information. So on one hand, we have the hosts that are providing data, but also able to query it from the policy. As one of the very central things in CF Engine is that all of the information that is available in the system is available to you to draw charts and print reports and do whatever you need to do, but also is available at the policy level so that your configuration management policy can make intelligent decisions or informed decisions at least about what to do based on the current conditions of your infrastructure and what it's doing. So we have the hosts both consuming and providing data. We have a nice graphical interface that I can show you a screenshot in a moment. But we also have in the back end your existing CMDB, your existing inventory database, your existing systems that you have built or purchased or whatever you're using. And you can also both contribute and consume data from that. So what I did here was overlay some of Mike's drawings on this architecture so that you could sort of see how this would all fit together. So we have the data production part on both sides. We can have hosts contributing data, still contributing data directly, and also the policy server contributing maybe aggregated or higher level data to the cache. Then we could have the CF Engine server consuming data from the entire data collection and management infrastructure to augment its own knowledge of the system. And of course, we have a nice, pretty user interface through which you can query things, again, in addition to using it from your own policies to drive some of the decisions that you make. So this is basically it. I mean, this is the main message that I want to convey, is that we're trying to make CF Engine play nicely with the infrastructure that you may already have. Just to show you a couple of things, the screenshot for the user interface in a larger, more beautiful detail, and a snapshot of the current state of a dashboard that is also coming up, where you will be able to see nice, beautiful metrics about the state of the infrastructure. So with that, I'll stop. We have a few minutes still for questions. I would like to invite you to our BOF tonight, if you are free around 8:30, I think, p.m. Come by, say hi, and we'll be around. We also have a booth downstairs, so if you want to come by. Questions?
I have a question. I may have missed it because I was concentrating too much. How do you deal with freshness of the data?
I'm sorry, can you repeat that?
How do you deal with freshness of the data that's being collected?
Yeah, so when we insert data into our cache, we set a time to live of 60 minutes. So if our clients are executing every 5 minutes, that gives them 12 attempts,
chances.
12 chances to insert into the cache. After an hour, the machine drops out of the cache, and we use our inventory database as a source of truth of what should be online compared to what's actually responding into the cache. And every day, our on-call pager basically gets a list of machines that 5 hosts fell out of the cache last night, and that's what we end up recovering. So the time to live is critical, because if we don't have a time to live and we don't allow objects to fall out of the cache, machines could change host names, we could move hardware from data center A to data center B, and we end up with this inconsistent state of what should be the truth. So the time to live actually works for us quite well.
Thank you. Another question.
So you were saying that this is used by people to verify that their input into the change management system, configuration management system, actually made it out to the right machines.
Correct.
So the way I would think of doing that would be to essentially look for the change I wanted between new and old.
Yes,
And
that's
and
what...
is there history in this system? Because you're talking about TTL here.
We do maintain a history. So the way we've maintained history is we've leveraged ZFS. We have this in-memory cache. We have basically a Python process that crawls the complete cache, dumps it to a ZFS volume, and every hour we take ZFS snapshots. So the majority of the data is not changing. Etsy password, maybe a user gets added, but the amount of delta is very small. This is where ZFS snapshots and deduplication becomes extremely efficient. We're finding that we have a 1 terabyte storage pool, and we've taken 200 days of snapshots over all of our infrastructure, and we're still about 50% utilization.
Okay, thanks.
But yeah, ZFS is how we're doing history. But this is how users figure out what automation changes that they want to request. So for example, Apache's not staying online on our web servers. They can use this to extract the process table, submit a request to us to say, make sure Apache stays up on the web servers, and then after we push the automation change, they can use this to say, Apache's online on all of our expected machines.
Okay, thanks.
I have one more question if nobody else does.
Sure.
Visualization, particularly of yours, of what you've done with Redis. How do the users get a report out of a result back? Is it just raw data that they process themselves, or have you got a dashboard?
Right now, everything is command line driven. Like I said, the heart of this project is a Python object called cache extractor. And a bunch of higher level utilities can be built on top of this. So for example, say you wanted to report on where Mike Sabota has sudo to root on which machines. So using the cache extractor object, we can search for the sudoers file, we can display the contents, we can programmatically go through this data and basically build a report at the end of it. So no, there's no web UI, there's no graphical user interface, but we do use this to programmatically extract whatever question we have at LinkedIn. I don't know if that answers your question or not.
Yeah, close enough. It sounds like it's flexible enough that a user could do this themselves.
Yes, if you wanted to build a web UI on top of it, it would be possible. And if it's open source, so if someone wants to do that, that would be awesome.
Another question.
Have you tried configure Puppet for your purpose?
I'm sorry, I didn't hear the question.
Have you tried to configure Puppet for this?
Have I tried to configure Puppet for this? CF Engine provides and meets our automation needs, so we haven't had to use Puppet or Chef or any other automation project. One really valuable concept that CF Engine provides here that is critical for this to work is the concept of splay time. So let's say our interval is 5 minutes. We're going to execute every 5 minutes. We set a splay time of 4 minutes. And if we have 5,000 machines, all of the machines basically are divided up into that 4-minute period, so they're not slamming Redis at once. And this is kind of a deficiency with remote command execution, is that if I use a product, for example, say Salt, to say, inject into Redis right now, and that hits 1,000 machines, all of a sudden 1,000 machines are hitting Redis all at once. So this is a great example of the maturity of CF Engine to see a concept such as splay time of how do I balance load from hitting other parts of infrastructure. So I hope that answers your question, but the architecture of CF Engine here just allows this to work flawlessly.
Okay, the second question.
You should be using CF Engine anyway.
Okay. The CF Engine, they have a dashboard for open source and community release, or just dedicated for enterprise customers?
So far, it's been available only in the enterprise version, but that's probably going to change in the near future. So I'm not at liberty of giving more information, but
there is a plan.
It's in the process of, yeah.
Any thoughts on Redis versus other key value stores?
You know, we looked at Memcache, we looked at Redis, and what was valuable for us here is really the dictionary or the hash, being able to uniquely find keys, search for keys. Have this already in Redis as native operations. So, you know, Redis has the keys command, which does exactly what I needed. I didn't have to build code on top of this. I could just focus on how to shard the data, how to collect all the sharded data back to build my complete working set, compression, stuff like this. I could focus on how to optimize this rather than the lower level building data structures. So Redis provided what we needed, so that's kind of why we chose it. But in this architecture, Redis is almost, if you think of like the OSI stack, Redis is almost like the network here. It's just the underlying transport. It just happens to be a very high performance key value store. So.
And just to address the last gentleman's question, the Puppet also has splay time, and the equivalent, I think, of this in the Puppet world would be M Collective, Marionette Collective, which does something, I think, very similar to your implementation, but of course for the Puppet world.
All right, there is another question, is there? No?
No, I thought someone raised their hand. No.
Okay, Mike, Diego, thank you very much for that talk.
Thank you everyone.